Hello everyone. So myself, Julian Fraise, and Kevin Raleigh from Stevens Institute are going to present. We both are going to speak, so I think we're going to kind of come to the podium when we're speaking. Yeah. So this is what's picking up the recording, right?
No.
Okay. So yeah, we need to present here. Okay. But you start. So
Yeah. So hi everyone.
you need to speak into the laptop because they're recording.
Like we just said, just 30 seconds ago. Hi everyone. I'm Kevin Raleigh, as he said, and this is Julian Fraise, and on behalf of our senior design team from Stevens, including our two mechanical engineering students, Stephanie Mallon and Luke Pacquiana, as well as an electrical engineering student, Juan Paul Sanchez, will be presenting to you today our research on a smart personal flotation device. So just to go over a little bit of our contents, how we'll run down this presentation, start with some background on our problem, how we're dealing with personal flotation devices, then on to our project summary, and then our concept prototype plan, including the electronics box and vest fabrication, how we calibrated our pressure sensors for depth, the system testing physically, numerical evaluation, and our suppression button demonstration, and then we'll tell you a little bit about what's happening next.
So I have to apologize because we aren't actually trying to sell you this currently, but we're going to give you sort of a tasty version. So I'll start with a quote to introduce the problem. The number of annual deaths worldwide due to drowning was estimated to be around 360,000 in the year 2015. This is a quote from the World Health Organization. Of these deaths, nearly 50% are boating related. So for boating accidents that resulted in the death of victims, 78% of the victims drowned, and 84% of those who died were not wearing life jackets. So let's talk about why people don't wear life jackets. The major quote, and what I hear about being a sailor and wearing a life jacket myself, is there's a lot of discomfort and inconvenience from wearing a life jacket, which is a terrible thing, especially when we're facing death as a consequence of potentially not wearing a life jacket. So we look at today's life jackets. Are they the final answer? That's the question our team posed. We think not. There are a number of issues with the current designs, citing unwanted inflation because the current automatic inflation type life jacket inflates with the contact to water. It's a chemical pill that activates and allows inflation at that time. This can happen with a really heavy splash. It can happen if you need to reach into the water and accidentally dip part of your body that has a sensor on it into the water. And you can become trapped under hulls if you're using small boats, and like if you've ever been canoeing, you can often get trapped under that, and the life jacket inflates and keeps you under there. And in order to self-rescue, people have to deflate or take their life jacket off to get out from under the hull, and then obviously that's not helping you, as well as hindering you, actually. And then there's this Islands Race incident in 2013. The Islands Race is a sailboat race off the coast of San Francisco. There was a crew, 5 people or 6. 5 entered the water in the incident. 4 cited their life jacket as rising up over their head, and the compartment shifted to one side, and somebody died in this incident. The body was found with this misplacement of the compartment. So we said, okay, maybe we should try and fix this, essentially. And we looked at the current market options. There are many things. There's the inherent type, the inherent buoyancy, the big orange thing that you find on the old boats, and the newer types that are manual inflation and automatic inflation. We looked at these because they're essentially the most comfortable and least inconvenient to wear, as they're out of the way as a sort of baseline product. This is an example of one here, the Mustang inflatable PFD. So Stevens had tried this project out a few times. They'd done some iterations investigating different parts of the solution. And there were 3 previous student teams from different departments at our school. This is a picture of one of the vests that they created as a prototype. So we kind of took this as a starting point and took their research and analyzed it for how we could do better and benefit from it. Yeah, still me. We've done this a lot of times, so forgive me. So our project goal is essentially our statement. Use modern technology to design and test a new vision of a personal flotation device. Right, we're engineers, we have tech backgrounds, we want to use what we know to solve this problem. The first major steps were a full literature review, both of the past Stevens work and of Coast Guard regulations, IMO regulations, the LSA life-saving appliance regulations on how the life jacket should be created. And then we came up with a system concept of what our life jacket would be. Like, if we could imagine a perfect life jacket, what would it be, and how are certain things being combated? So the electrical piece of our electrical part of our team developed the idea to implement a microcontroller and the corresponding circuit to read sensors, which can elaborate further for you a little bit, but essentially we monitor the pressure of the water to tell the depth in the water column, and we monitor the user's orientation, something we're using in our testing preliminarily and potentially implementing in the final design. The mechanical piece of our team developed a pneumatic system to handle the CO2 canisters and the CO2 passages for inflation of the compartments. Again, we can answer questions at the end, but we don't really further go into this because this wasn't our piece of the project. And so we've done a couple prototypes. The first step we're calling the systems prototype, where we laid out a couple major systems. We did a pressure sensor calibration, which we will go further into detail with. We have data analysis code completed. This is something that was started and helped along with our advisors. We'll show you some plots from this and how it's helping us determine if we're quantifiably better than anything before us. We developed a 4-bladder pneumatic circuit and electronics. We have a multiple compartment design. We'll go into why we think this could be better. And we developed a testing protocol practicing with existing vests from previous iteration of the project, and our updated electronics to gather the data we wanted. So we've now moved on to this concept prototype where we're testing currently. We're trying to improve on the results from systems testing to show the advantages of the inflation sequence and of the multi-bladder design, seeing if it is better and how it might be tested to show such. And we're trying to incorporate this user suppression option to delay the inflation, right? So we have to set some threshold for when the life jacket should inflate. And we want to be able to let the user say, look, I've jumped in the water to save my child. I don't want this to blow up in my face. I'd like to be able to swim down a little bit more. So we're trying to work on how that's going to be implemented, but details are still to be developed with that.
All right, so again, to go over a little bit of what we're going to talk about in the next few slides. First, we're going to talk about our concept vest and that prototype, including the box, which is waterproof to house the electronics, and then move on to our pressure sensor calibration. As I said, we've got a pressure sensor on board to measure depth for testing purposes, and then talk about some of our additional physical testing, the tests that we've done with our previous vests with 2 compartments, 2 air bladders on board, and then talk about a little bit of our numerical evaluation, what we've done and what we hope to do with it, and then talk about our electrical circuit and show the suppression button switch. We've tested an electrical board, and we've also tested this switch functionality, and we'll show you a video of that a little bit down the line. So as far as the fabrication of the vest and the electronics box, what you see there on the left is our latest vest prototype. It's a 4-bladder design. The 1 bladder that you can't see is behind the neck to support the head in the floating state. Each of these bladders folds out. They're Velcroed down right now to give it a compact and more comfortable design. So they, when inflated, will reach their full size and right the user. And next to that, you can see our fully opened electronics box. It's a waterproof housing that allows for all the CO2 connections, this giant battery that we're using for testing, our valves, and then the different circuitry up in the top half of the box. This is our current state of the electronics box, and obviously we'd like to reduce that size quite a bit, but this is what's really necessary for testing over and over again. And then in a future design, we'd like to shrink this down and make the circuit and the batteries and everything like that more compact. So moving on to our pressure sensor. So we had to obviously calibrate this sensor to make sure that we were getting an accurate depth. So what we did was we mounted our box onto this plate using a 3-point mounting so that we were sure it was raising and lowering in a way that we could accurately measure that depth. This line is attached to 3 loops of rope, which we hooked above our tank to ensure that we were meeting the same depths every single time. It was lowered into the water to 4 different depths, brought back up, and then lowered again repeatedly to show that we were getting the same values no matter how many times it was lifted up and down. And then we were using material that we had in our lab to test this. So what you see here is our filtered data. So obviously as the depth increases, the voltage also increases. So you see it getting deeper into the tank, raised back up, deeper into the tank, so that we do have that repeatability. So each of those flat horizontal parts are where we were holding it to ensure that we were getting the same reading over a steady state. From that calibration, we could fit the voltage against the depth so that we could ensure that we weren't, that we had a proper trend. We expected it to be linear, and it was. So as compared to a previous pressure sensor which we were using, we had a standard deviation on that one of 0.35 meters, so quite a bit of variation, which led to some wonky data in our tests. And the new sensor we've got calibrated so that it's within 0.06 meters, so really a lot more accurate with our depth sensing.
Okay, maybe we don't have a video for you. It could be that this is the PFD and not the PowerPoint. Regardless, so we did some initial testing on a previous vest configuration. This was a front compartment and a back compartment linked together but separated so that they could be inflated at varying times. And this awesome looking orange thing is our test mannequin. It's something repurposed for lifeguard training. It's weighted to the weight of a human when filled with water, density of a human. So we used this and ballasted it so that it would sink to the bottom of our tank in a face-down orientation, and we could use the pressure sensor to initialize the vest inflation, and we could test the rotation of the body as it came to the surface and the time it took to rotate and come to the surface. So what we did here was some repeatability testing. We only tested simultaneous inflation. We have done some testing with a delta T introduced between the inflation of the 2 compartments. That data was somewhat inaccurate, so we're redoing this testing, but we have some of this data to present to you here. So what you can see is some data collected from our microcontroller and data collecting unit, and then post-processed. I'm sorry about some of the text here. Again, I think it's a PDF instead of a PowerPoint. But on the left, you have body depth and orientation versus time. So the black line in the left graph is the user step. This is overlaid by an image of a rectangle which represents the body with the 3 axes coming out of it. So you can see the red is face forward off the body, the blue is upward, and the green is arbitrarily to the left of the body. So this body rotates face down, red pointing down at the bottom of the tank. The black dotted line is the threshold for inflation depth. So it reaches that point, there's a delta T between it reaching that point and the inflation. The blue dotted vertical line is the instance of inflation or activation of the bladders, and they take a moment to react, and then you can see the body rising to the surface and resting at its steady state, which I would have loved to show you in a video. It's pretty cool. On the right here we have inclination versus time. So the black line is what I'm referring to as inclination. This is the local x coordinate of the body versus the global z coordinate, so that we have something that relates to the LSA guidelines for the inclination of the user. They specify that the inclination needs to reach minus 20 degrees from the vertical, so the user has to be tilted back in a way such that their mouth is up and away from the water. That is represented by this black dotted line in the right graph. So we tested the time from activation of the bladders to this proper inclination as a matrix result, and we're going to look at some of the results here. We also overlaid the compiled pressure plots from the time of activation to the body reaching the surface of our comparison runs. These data are shown in the chart down below. So we collected a standard deviation to see how close and how repeatable the data was. For our time to inclination, the standard deviation was found to be 0.9 seconds, and the time to surface was found to be 0.3 seconds. We'll talk about what that meant for us. And essentially, the conclusion we drew was that the time to surface is repeatable for our purposes in that we're trying to test delta T between compartments, and we were seeing in our initial delta T trials a significantly larger time difference than 0.3 seconds between time to surface for delta T versus a simultaneous run. So we accepted this standard deviation. We had a larger standard deviation with time to inclination, and it showed variability. So we're looking at the metric that we're using. Minus 20 degrees, for instance, is supposed to be the steady state of the body, but that's not necessarily anything in our minds for what we're testing. We just need a metric for how quickly the body orients itself. So we may change this, and we're looking into that currently. Yeah, so delta T testing for this 2-compartment vest is being run currently. There are a lot of tests run at Stevens, so we get to fit in there with the other senior design groups. But the vest will hope to be used as a comparison between this and our beta test. We can't actually incorporate our electronics onto a market design, though this would be ideal because then that geometry is what we could compare to. So we are looking into that, but it's harder and there are hurdles to get over with that.
Right, so as Julian just mentioned, what we really want to do is be able to compare our life vest to what's on the market right now and to other designs, previous designs and other historical designs. So we want to do that both physically, and then we want to confirm those results numerically. So the first way that we attempted to do this was using the Rhino modeling software with the Orca plugin for hydrostatics. So what you see here is our three-dimensional man that we inherited from a previous design team, and onto him we've added a sort of old-fashioned inherently buoyant PFD, and then compared that to our smart PFD concept, and we did this so that we could try to run the hydrostatics in Orca to see how the body would write with the different layouts of the bladders or the inherently buoyant life vest type. We ran into a few issues with Rhino and the way that it modeled a human being that we tried to work out, but it would really rather have a ship than this guy. So we're working right now on a MATLAB script which will do essentially the same thing and calculate the writing forces and see how that body would react to wearing a different life vest design. This slide, similar to the previous testing, should have had a video, but essentially what it had next to this image of a button was our suppression button system, and what that is as we mentioned at the very beginning, very often with current automatic inflation, you get into the water and you don't necessarily want your life vest to go off. So if your life vest gives you a warning and you can hit a button somewhere on the torso or on the body to delay that activation, in the case that you're fully conscious and perhaps you're just reaching into the water, or perhaps you want to dive to a certain depth or something like that. This suppression button idea will let the user delay that activation until prompted again. We're currently working with what that time delay should be, if it should be 10 seconds or 30 seconds, wait a minute. But essentially, if there's no input from the user, the life vest will assume that the person is unconscious and write the body, activate inflation. So what we're working on next, we're trying to test our system prototype with different delta T staggered inflation sequences, and then move on to our concept prototype to get some comparison data between the 2-compartment and the 4-compartment vests. And then we're hoping to incorporate that suppression button onto our actual electronics box or onto the vest itself in such a way that it's more useful than just having a free hanging button. And then we'd like to potentially perform a full functional test on a person. So far there's only 2 volunteers and you're looking at them. But that is our presentation. Thank you very much, and if you have any questions, we'd be happy to answer them. Yes?
You talked about integrating smart features into your inflation mechanism. You got your suppression button. I'm curious if you considered any incidents in recent years, specifically in 2011, the wing nuts incident and the Rambler incident, in terms of being underneath an capsized vessel, maybe being unconscious and having your life jacket go off and being stuck underneath it, even though you're unconscious.
Right, so there's a lot to work with. Right now, a lot of what we've done is getting this design to work, but then there's going to be a long step of deciding what sort of parameters will determine activation. Right now, as you saw from our testing diagrams, it would have been easier with the video. How we have it is that when the body's face down on the bottom of our testing tank, it activates and it comes back up. But we sort of have to have a long discussion about what sort of parameters will initiate the automatic activation, and then what sort of parameters will come into account when it comes to this suppression button type of idea. So it's definitely something that we're considering because this problem is fairly complex, and there are always going to be exceptions to a person just unconscious in open water, as opposed to under a hull, or maybe their vest gets caught on something beneath a wave or something like that. It's definitely something that we're considering. Yes.
I'd highly recommend that you guys talk to the Storm Crossing Club about their parameters for going electric. It's very easy to research.
Okay, great. Thank you very much. Yes.
How about regulatory input? I think I heard LSA, I'm not sure what that is, but like the Coast Guard. You've got a lot of electronics and control here. How does that fit into all of this?
Right. Okay, maybe I can, because I have a pun for this. As far as we're concerned, it's uncharted waters, right? So we looked into as much as we could find from the Coast Guard about regulations for PFDs. We had to look elsewhere. LSA is life-saving appliances. They at least gave us some specifications for the state that the life vest or life-saving appliance needs to put the user in at the surface. The Coast Guard was pretty unclear. They basically give you buoyancy, and if it's inflatable, it has to have this buoyancy. Yes, I certainly worry about wearing electronics on me in the water. We have problems with the water reaching our electronics in a very controlled environment, but the point is to prove it, and sometimes you need to venture outside what seems reasonable at the time, right? So we think about it. We didn't see anything in terms of regulations in electronics. Yes.
Such research are eventually for some commercial operation, commercial application. So how do you protect your research even at this very early stages?
Yeah, so we should worry about people taking the ideas right, but we have a lot of ideas, and it's really hard to make it come to fruition. So right now we're a long way off from anything truly being realized. We're trying to show that this is better. If we see that this is markedly better, we should maybe take a step back, looking at my advisor right now, and worry about people bouncing off of what we've done so far. But up to this point, we haven't had anybody say, I'm going to take this research, and maybe we should be more worried about it. So thank you for the heads up.
I'll keep it in your mind.
Okay.
You'll be surprised how some of this type of research eventually will become full-scale application.
Right. Yeah. We have part of this project is developing a business plan, right? And it's somewhat viable in a market if we solve this problem in a good way. So there's definitely an application for this. Right. In the back, yes. I'll just repeat. The question was whether or not it was integrated into a survival suit at all, if it's a separate system or if it's combined. That's not any part of our design. We totally could look into that. Survival suit being something you wear when you're entering cold waters and going to be in the water for a long time, right? Yeah, that's potentially a very good application for this technology, especially because we would worry less about bulk at that point.
They have on trains, they have what they call the dead man switch. If the engineer has a heart attack, apparently the train is supposed to stop. I would imagine because of the electronics in this, that you want to have some kind of a mechanism that if the electronics fail, it should automatically.
Sure, so if the person's in the water and the battery's running down, it will be put into an inflation sequence. There's also oral inflation, like there are on current market options, and we are working on the mechanical inflation. We're just bouncing between a lot of pneumatic systems right now, but Yes, that's totally in this area of we need to make it work and see that it's beneficial to continue doing our work, and then thank you, and we have thought about that kind of.
Okay, thank you very much.